Okay, so in this video, we are going to prove that all three of these are equal to each other using the different theorems that we identified. So our given is what we're given up here. We're given that triangle ABC is isosceles. With AB is congruent to AC. We also know, and I'm sorry, I did not leave enough room, so I'm going to finish my given over here. We also know that CD bisects angle ACB and BE bisects angle ABC. Now the definition of what it means to bisect is on your actual handout. It says a ray in the interior of an angle creating two congruent angles. So you know those two angles will become congruent, and that's important. What we want to prove is that triangle AEB is congruent to triangle ADC. And then we're going to become those little overachievers and prove that triangle BDC is congruent to triangle CEB. And then finally, prove that DFB is congruent to triangle EFC. I would never expect you to do this on tests. Too much writing. But proving that one set is would be sufficient. But we're just going to do them all so you can see how we build from the previous elements that we proved. So the very first statement would just be our given, okay? Which we do have to write again. So triangle ABC is isosceles with AB is congruent to AC. CD bisects angle ACB, and BE bisects angle ABC. That's our given. Now, if we know that we have an isosceles triangle, we know that the base angles are congruent. That's a property that follows. So that's going to be the very next thing that we state. And we need that in order to show that all of those little angles at the bottom are congruent to each other. While we know that these bisect, and we know that each of these are equal to each other, the fact that the base angles themselves are equal to each other are going to allow us to show that all four of them are congruent to each other. So angle ABC is congruent to angle ACB. So we're just proving that this overall angle is equal to that one, and that's because base angles of isosceles triangles are congruent. Remember, an isosceles triangle, the definition just says that it's a triangle with two congruent sides. So the fact that the base angles are congruent, that's not part of the definition. That's a property that follows. Let's say you just put your definition of isosceles triangle. Am I going to take everything off? No, but it might take off a couple points because that's not actually the definition. That's a property that follows, and it's on your definition and properties handout that you have. Okay, if we know that these two little lines bisect these guys, then here's what we know next. By definition of bisector, that ABC or angle ABC, it's congruent to 2 times ABE, and angle ACB is congruent to 2 ACD. Because why am I doing this and writing it in this way? Because I need to prove that these two guys are equal to each other so that I can actually use angle side angle. If I express it in this way and I already know these two are equal to each other, I can substitute and use the property of division to simplify. So this is definition of angle bisector. So by substitution, we can say that 2 ABE is congruent to 2 ACD. And then by the division property of equality, we can just say that angle ABE is congruent to angle ACD and again, these properties are on that handout that I've given you that is in blue, which you'll get to have for the test, but you need to practice applying them. Okay, we have now shown that what? Here's what we've shown. We know that since this is isosceles, you already have two sides that are equal to each other. You now have proven two angles. The other angle that you want to prove is just that A is equal to itself. That's the reflexive. So angle A is congruent to angle A. That's reflexive property, my favorite property in the whole wide world. So you have now shown angle side angle, so you can then say that triangle AED is congruent to triangle ADC. And that's by angle side angle. Alrighty, we are going to move over to these two little guys right here. Now, the easiest one again, by reflexive property, would be that BC is equal to BC. The other thing that we now know is that DC is equal to BC because corresponding parts of congruent triangles are congruent. So you could write either property first. I'll go ahead and do the congruent parts of congruent triangles are congruent just because I like to write the letters. So DC is equal to EB by the theorem that congruent parts of congruent triangles are congruent. And then we know that BC is congruent to BC by reflexive property. So what are we left with? You have to prove that these two little angles are equal to each other. Well, here's the good news. You know that these two that you've already shown are equal also equaled the angle that's right next to it that was bisected by the definition of angle bisector. So you just say this one is equal to that one, this one is equal to that one, and since these two are equal by substitution, those two are equal. Okay, so it's not so bad. So angle ABE is congruent to angle EBC, and angle ACD is congruent to DCB, and that is just by definition of angle bisector. Then by substitution we can say that angle EBC is congruent to angle DCB, and that again is by side angle side. Oh, I'm sorry. No, that is not by side angle side. That's substitution. But we know that triangle BDC is congruent to triangle CEB by side angle side. All right, the last little triangle should be nice and easy because we've proven almost everything. These two little guys. Well, you know these two angles are equal to each other because vertical angles are congruent. These two sides are equal by corresponding parts of congruent triangles are congruent. So you just have one other thing left to prove, or do you? These two angles. Haven't you already shown that those are congruent? Yes, you have. You did it way back up here. So you don't have to reprove it. It's already done. So you just have to show those two things and you're good to go. So we know that DB is congruent to EC because corresponding parts of congruent triangles are congruent. We know that DFB is congruent to EFC because vertical angles are congruent. Notice my shorthand's getting shorter and shorter. And then lastly, triangle DFB is congruent to triangle EFC by what? By angle side. Okay, we did it. Triangle congruence relationships are building blocks for many geometric concepts and proofs. One important concept related to proving triangle congruence is the concept of sufficiency. That is identifying which conditions are just enough to ensure that two triangles are congruent. For example, side angle side is just enough. Side side is insufficient. In addition to side side, what other correspondences of congruent parts between two triangles are insufficient to prove two triangles are congruent? Well, one is angle angle, or even angle angle angle. Why? Because you can have the same angles, but one be a dilation of the other. Those would be similar, but they wouldn't be congruent. The other one is side side angle. And if you think about that, you could do a little drawing of something like this, where you know these two sides are congruent in this angle. But what you could have is a triangle that looks like this, where you kind of swing this out further, but it maintains that same length. These are two totally different triangles, even though they have two sides that are equivalent and an angle. It's that swinging of that leg out and the fact that you can maintain all these other congruences that mean that this would be insufficient, because you could have a totally different triangle. When you're looking at your congruence handout, the correspondences of congruent parts between two triangles that are just enough are these guys. Side, 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 angle, side, side, angle, angle, side, and then lastly, hypotenuse leg. And that hypotenuse leg is unique to right triangles, and we're going to talk about that in the next video.